Hello. Today we're going to learn about scale factors and volumes and areas and so on. And so by the end of the day, I hope you'll be able to say I can use scale factors in different dimensions in similar solids. I can identify the scale factor for length, area, and volume of similar solids, and you can explain the relationship between scale factors of areas and volumes. Now, before I start up and really get into the lesson, this is just an extension from a previous lesson. A couple chapters ago, or I guess it was the area chapter, we learned something about scale factor of similar areas. So if I have something like this, and if it's similar, let's make it half the size. Uh, Say if this is 3 and 1, and I double the size, so this is 6 and 2. We asked the question, if I double the size, what happens to the area? Does it double the area? And if you look at this, 6 times 2 is 12. 3 times 1 is 3. And this is for area. And so we noticed that if we double the sides, we don't double the area. What happens to the area is it's multiplied by 4. So we did times 4. And we investigated this a little further, and we saw that whenever I multiply by my sides, I'm going to square to get this. So if I would multiply my sides by 3, then let's try that. So if I multiply the sides by 3, this would be 9 and 3. So now I'm changing this to multiplying by 3. So if I multiply the sides by 3, this area becomes 27, and this area is still 3. So now it's not 4 times as big, it's 9 times as big, because 9 times 3 is 27. So what I multiply by the sides, I square it 3 times 3 to get what I multiply by the areas. So we're just going to extend this for the day to volume. Now, if we extend that to volume, if we have these two similar rectangular prisms, we want to, and this one is twice the dimensions, 2, 2, 4 of this one, 1, 1, 2. How many of these little ones will fit in this big one? Well, we could take this, and you would think you could move it. There we go. And that would just be in the back corner. I can move another one here, and then another one up here, and then another one in this corner. So there would be 4 on the bottom, and hopefully you see there's 2 rows, so there would be 8. So a way to visualize it, this might even be harder to see. I tried to color them all different colors, but if I take these out, you can see that there's 4 on the bottom, and there's going to be 4 more on top. Great. So now we know that if I find the volume here, I get 2. If I find the volume here, I get 16, which is 8 times as big. Or that's another way of saying 8 of these fit in here. So when I multiply the sides by 2, the volume gets multiplied by 8. Now let's think about the connection between 2 and 8. Let's try one more and see how this looks. Are these objects similar? What ratios do they have? So if I take 4 divided by 3, you should get 1.3 repeating. If I take 16 divided by 12, do I get that same answer? Hopefully. What about 2 divided by 1.5? I get the same answer. So the question says, are they similar? Yes, they're similar. The ratio is 4 to 3, or 1.6 repeating. Both those would be acceptable ratios. All right, now it says find the volumes of each of them. So we're going to find the volume of the big. So if I do the area of the base, 4 times 16. 4 times 16 is 64. And then I take 64 times 2, because that's the height. So volume of big is 128 centimeters cubed. All right, so now we just got to find the volume of the small. And we have 3 times 12, which is 36. 36 times 1.5, and we get 54 centimeters cubed. All right. So that's the ratio that we have the big one, we have the small one. The ratio of their volumes. Well, the ratio of volumes equals 128 to 54. And let's reduce that. If I divide both those, that would be 64. If we divide them by 2, that would be 27. So 64 to 27. Now that can't divide by any numbers this can, so that's as reduced as it gets. 64 to 27. So how does the ratio of the volumes compare to the ratio of the sides? So I have a ratio of volumes equals 64 to 27, and ratio of sides equals 4 to 3. Well, if you think about this for a while, 4 times 4 is 16. 16 times 4 is 64. So 4 cubed is 64. And 3 times 3 times 3 gets us to 27. So I just have to take my ratio of the sides and cube it to get to ratio of volumes. So here's our formulas. Like I said in the beginning, with areas or surface areas or anything like that, if I take the scale factor of the sides and square it, I get the scale factor for the surface areas. But if I take the scale factor for the sides and cube it, I'll get the scale factor for volumes. So that's our formula. They should pause it to make sure everybody has that written down, and we'll move on. All right. Now, if I have these figures, they're similar figures. If I want to find the ratio of the sides, surface areas, and volumes. The ratio of the sides, 9 to 4. I'm going to use a different color just for fun. I'm going to say that's 9 to 4. And then the surface areas, we just have to square it. 81 to 16. Now, if I want to find the ratio of volumes, I just have to cube, 729 to 64. Now I have all those ratios. Now, if I wanted to find a certain diameter or something here, and I knew the other one, I would use the ratio of sides. If I wanted to find anything with areas or surface areas, I would use this ratio. But if I wanted to find volumes, I would use the final ratio. So it depends on which thing you have in order to solve for the missing values. This one says, find the volume of the larger rectangular prism if the smaller rectangular prism has a volume of 24 centimeters cubed. So if we look at this, we know the ratio of sides is equal to 2 to 3, because we have a 2 to 3. Now if I want to set up a ratio here, we first need to find the ratio of volumes. Ratio of volumes is those numbers cubed. So 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. Now, we know that the volume of the smaller rectangular prism is 24. So I'm going to come to my pen. I know ratio of volumes is 8 to 27. And I'm going to set up the smaller one that has 24. So I'm going to do 24 over x. So now I cross multiply and divide. So I have 24 times 27 and divide that by 8 to get x equals 81. So the volume of the bigger one is 81 centimeters cubed. Let's look at the next one. Two similar prisms have a ratio of their surface areas to be 16 to 9. So I know the ratio of areas equals 16 to 9. What's the ratio of the sides? So to find the ratio of sides, what we do is we square root each of those. So 4, 2, 3, and we're done. Two similar pentagons have ratio of the sides to be 4 to 3. So ratio of sides equals 4 to 3. The ratio of the volumes equals both those numbers cubed. So 4 times 4 times 4, 3 times 3 times 3, and we have the answer. All right, now it's going to get trickier in a second. If two rectangular prisms have a ratio of their surface areas to be 9 to 90 or to 49, what's the ratio of their volumes? So the ratio of areas is 9 to 49. So we can't go straight to volumes, but we can do the ratio of sides is equal to the square root of that, which would be 3 to 7. Once I have the ratio of the sides, I can find the ratio of the volumes by cubing that number. So if I cube 3, I get to 27. If I cube 7, I get to 343. I have to, yeah. All right. So that's how we go back and forth between these different ratios. Now, sometimes we have to use the certain ratios, like in this problem. Two similar rectangular prisms have a ratio of their surface areas to be 9 to 49. The smaller prism has a base length of 10. What is the base length of the larger prism? So the ratio of areas equals 9 to 49. The ratio of sides, or that's all lengths, will be the square root of those. So that's 3 to 7. So now it says we're looking for the base length. So lengths, we'll use the ratio of the sides. So we'll set this up saying 3 over 7 is equal to, the smaller one has a base length of 10. So the smaller one in this case goes on top because 3 is on top. So 10 over x. So now we'll cross multiply. 10 times 7. Now divide that by 3. And x equals 23.3 repeating. Or we could just put a bar on the top there. All right. Now, if we have the same situation, but now the smaller prism has a base area of 40 centimeters squared, we can take the same information here, pull it up. We have a ratio of sides and ratio of areas. Now, since we're looking for an area, we use 9 to 49. So I have 9 over 49 is equal to, the smaller one has a base area of 40. So the smaller one, this goes up here, 40 over x. So now when I cross multiply, I have 49 times 40. Divide that by 9, and x is 21.7 repeating. No, not 21, 217.7 repeating. Now if we have that same situation, but now we want to deal with the volume. Now what we have to do is find the ratio of volume. Now 3 cubed is 27. 7 cubed is 343. So the smaller prism has a volume of 400. So since it's volume, this is the ratio we're looking at. And the smaller prism has a volume of 400. And x, and now we just cross multiply. 400 times 343, divide that by 27, and the volume is quite big. Volume equals 5,081.48 centimeters cubed. All right, now we'll finish this thing off with the success criteria. Two cones have a ratio of their volumes to be 343 to 729. What is the surface area of the smaller cone if the larger cone has a surface area of 100 centimeters squared? So what I'm going to do is take this, throw it over here, and get rid of the numbers. So the ratio of volume is 343 to 729. If I cube root that, using the cube root function on a calculator, that's going to be 7 to 9. And the ratio of areas, I have to square that to get 49 to 81. So now, what's the surface area of the smaller cone if the larger one has a surface area of 100 centimeters squared? This is what I use. So I'm going to have 49. Oops. I'll try 49 over 81 and set that equal to the larger one has a surface area of 100. And so that's 100, and I'll put an X here. Now I can cross multiply. That's an equal sign. 49 times 100 divided by 81, I get 60.5. So my new area is 60.5 centimeters squared. Well, I hope that makes sense. Good luck on the assignment.